Let's talk about chapter 16. Chapter 16. Earthquakes. Earthquakes get their own chapter. You can probably guess why. They are damaging and they heavily affect society. But they also do something really interesting on top of sort of just being this destructive natural disaster. They sort of let us study the interior of the Earth. But anyway, if you want an official definition, it's the trembling or the shaking of the ground caused by the sudden release of energy stored in the Earth's surface. And it's released, this energy that's released is released in the form of seismic waves. So there are waves that travel through the ground due to these earthquakes. It's like if you hit the edge of a table and you hear the table like reverberate, or you slap your hand on the water of a pool and you can see the waves move out from where you hit the water. Seismic waves are basically the same thing. It happens when there's a release of pressure along a fault. So in chapter 15, you learned all about faults, all the different types of faults, but the movement along the fault when these things happen is what generates the earthquake. It's that release of energy. So here there's a fault that hasn't gone off in a while, and there's enough pressure here that boom, the fault ruptures and we get an earthquake down here at the exact point that it's sort of ruptured at. And here we can see, the offset of this this fence post, or this fence line that used to be connected together due to the earthquake that occurred along the fault that would probably be running right through here. So there are different parts of along a fault when an earthquake happens. There's the epicenter, which is what we usually hear on the news, but there's also the focus, or the hypocenter. The focus is actually the point of the breakage. It's where it originates, and that will actually be down in the ground somewhere. The epicenter is the part that's on top of that focus. So, the earthquake didn't start here at the epicenter. It started at the focus. And sometimes these focuses, or foci, will happen deep, deep, deep in the earth. And when that occurs, sometimes you may hear about a really, powerful earthquake, like a 7.5 or something. But if the focus is so far down in the earth, it's got a lot of rock to travel through. It may actually not be as devastating as on the surface as it could be if that earthquake had occurred, up here somewhere. Especially when you're talking about tsunamis. A lot of times I'll hear about a large earthquake happening in the ocean somewhere, or in the crust under the ocean somewhere. And one of the first things I'll look for is what's the depth of that earthquake, because in order to get a tsunami, you have to have a lot of offset on the surface like this. And if it's too deep, you're just not going to get that offset to push the water up that exists, up here if this was the ocean. Anyway, getting off topic. So, there's two main types of seismic waves that occur whenever there's an earthquake. There's the body waves, and there's the surface waves. And it's not going to be super important to me that you know the different types of surface waves, at least not right now. But the body waves are a little more are important. So the surface waves occur from the epicenter out. They occur along the surface, and the body waves are actually coming out from the focus. So let's talk about body waves. So one's the P wave, and one is the S wave. The P wave is the primary wave. It is faster, and it actually moves a little bit faster through the rock compared to the S wave, which is called a shear wave. Also, sometimes you hear people call it the secondary wave, so either or. And it moves a little bit slower, so it arrives after the P wave. And this relationship that they have to each other, the fact that the P waves show up first and the S waves show up second, we can use that knowledge, that information, to help us determine where an earthquake actually occurs. More on that later. But one of the really interesting things about P waves and S waves is P waves will travel through solids and fluids, and S wave will only travel through solids. So let me show you. And if we were in class right now, I'd actually I pull out a slinky and we play with a slinky. But I've got a little picture here. We can talk about that. So ignore this for now. But first off, here's a primary wave or a P wave up here, and down here is a secondary wave or an S wave. So if we had a slinky and I wanted to show you guys how P wave moves, I'd push that slinky in on itself, and you'd see this pulse move back and forth along the slinky. And another way to think about this, and remember, P waves will travel through solids and liquids. If we were both in a pool, like a swimming pool together, and underneath the swimming pool I pushed the water, you could feel me pushing the water towards you. If we were standing next to each other in the pool, you could feel that pulse of water that I pushed. That's kind of how this stuff is able to move through liquids. Secondary waves, if I had a slinky, here it's a rope, but if I had a slinky or the rope, and I just shook it up and down, you'd see this sort of zigzag move back and forth along the rope or the slinky. But if you think about how we're in a pool, I can't really shake the water, so this doesn't really work in a liquid, but it works in a solid. Why do we care? Why is that important? Well, if we think about the interior of the Earth, and we'll talk more about the interior of the Earth in a later chapter, we think that the core, part of the core, is liquid. The reason we think that is because we can look at these waves, these P waves and these S waves, we can sort of listen for them, and when we listen for them, and again, I'll be more I'll display this farther later on when we get in a different chapter, but basically those P waves can get pushed through a liquid and we can listen for them on the other side of the planet, and it's a way for us to determine, and it's why we think that part of the core is liquid. It's not that we've ever drilled down to the middle of a planet. We can't do that. We can only drill down a few miles. We can't drill down thousands of miles. But we can listen to these earthquakes. And an earthquake it's basically like a sonar ping that goes through the planet, and we can listen to them, which is kind of what makes them so fascinating or so useful. Yeah, they're super destructive, but it's a way for us to determine what's going on underneath our feet and what's down there. And it's a massive, massive science all on its own, having to deal with geophysics. But again, or seismology and geophysics. But again, we'll talk about that later. So I cross this out. I'll go ahead and keep it there. So this is also talking about surface waves. And so surface waves are the stuff that occur on the surface. So here we're showing a love wave and a relay wave. This is not super important to me that you know the difference between these two. Really what's important is these waves, these surface waves, it's the stuff that does the damage. These P waves and S waves don't really do any damage. However, you can feel them, and it'll kind of potentially tell you that a larger shaking is coming, or at least you can detect them. But these love waves and these relay waves are what does a lot of damage on the surface. And these are videos that I'm not going to play right now, but it just shows the love waves and the relay waves. So how do we measure these things? I don't care that you know the difference between all these three things. I just kind of want you to know that they exist and how this stuff works. So there's seismometers, which is basically the meter. That's the thing to use. That's the device that's used to measure these seismic waves. It's the little it's this thing. There's seismograms or seismographs, which are the devices used to record it, and the seismogram, which is basically the piece of paper that it's drawn on. So basically what it is, it's this thing that's situated to the ground. And again, this is kind of how it was used to done, and I'm sure there's still some out there that operate like this, but now this is mostly done digitally, and we don't use this. But essentially, you've got a weight on a spring, and when there's an earthquake and things shake, it draws the zigzags on the paper, and this paper is slowly moving at a constant rate. And in the past, you'd have to go change out your paper every now and then. So, why did I tell you about this? So this stuff will measure, will sort of measure these different waves as they arrive. So there's the P wave again. It's compressional, like I showed you with the slinky. It is the first to arrive, and it is the fastest. So it'll be the first thing that shows up on your seismometer. The S wave, it's the second to arrive, and it can't pass through liquid again. But the difference between the timing between these two can help tell you just how far away your earthquake actually occurred. And then there's the surface waves, which again are the relay and the love waves. They are the slowest and the last to show up. And they will show up in a big way on your seismogram. And again, they are the most damaging. So how can we use this stuff to actually figure out where an earthquake occurred? So we use what's called a travel time curve, and it's this thing down here that I kind of want you to look at, and there's a lot going on with it. But let's see, do I blow this up later on? I do, perfect. Well, first let's look at this. So here's an actual seismograph. And you see the squiggly lines. So here we see the first P wave show up, boom. And then you can see the S wave actually shows up here. And then the surface waves show up. You can see how big those zigzags get. But the difference between the arrival of these two waves can tell me how far away the earthquake actually occurred. Because my little seismometer here, it might be 500 miles away from where this earthquake occurred. And you see these little tick marks all through here? These little hash marks? These are usually 1 minute intervals. And the reason there's multiple lines is because this is how you get the seismograph. This is one continuous line, right? So you're going from 1 minute to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and on and on and on and on and on. Until you get down to here a couple hours later and you actually get an earthquake. So anyway, let's look at 3 seismographs, or seismograms, and here are the locations. This one's from Denver. This one is from St. John, which is in Canada. And this one is from Lima, Peru. And you'll see that there are these shorter intervals between when these two waves arrive, these two different waves arrive. Here this took 3 minutes, here this took 8 minutes, and here this took 12 minutes on this one. And we can graph these things out based on that difference. That'll tell me about how far away I am. And there's an equation for this. It'll tell me how far away I am from the epicenter, or the focus. So here this is 2,000 kilometers away. Here this one looks like it was about 5,000 and a little bit. And here's this one that was about 9,000 away. I don't know the direction though, right? This tells me, okay, from Denver there was an earthquake that was 2,000 kilometers away. Well, where? What direction? Well, if you remember when we talked about GPS satellites and how those work, how they have to do triangulation or trilateration, this is sort of the same thing. I can go to Denver, and if I get a map on Denver, then I can draw a big circle around Denver. That's 2,000 kilometers, and vice versa with these. So again, this is just kind of reiterating. We've got a couple of seismograms, and this sort of time lag here between the P wave and the S wave, and the time lag here, this seismogram, will tell me the rough distance. I can figure out the distance based on how fast these things travel, right? Because we know P waves travel at whatever it was, 5 kilometers per second or so. I think that was. We can go back to that slide, but I'm not going to. But we can use this to figure out roughly how far away these earthquakes occurred. So let's take a map. Here's Denver, and we would draw a circle. And we know that the earthquake happened somewhere in that circle, but we don't know where. Here's St. John. Again, we know that the earthquake happened somewhere in this circle, but we notice that these circles meet. And let me clean this up. We know that these circles meet here and here. So with only 2 locations, I know there's either an earthquake here and an earthquake here. But I need a third location to help me figure out which is which. So all three of them meet right here. Now, of course, you know, being geologists, we could, you know, do a little bit of hypothesizing. Let's say I only had Lima, and let's say I only had St. John, and so they meet up here and here. Well, this is not, you know, this is out in the middle of the oceanic crust. Maybe it's associated with the mid-oceanic ridges, I don't know. But over here, this is an active margin. We know there's a lot of subduction going on over here. There's volcanoes over here. I'd be able to, you know, kind of deduce that, okay, that's probably where the earthquake happened. But anyway, in reality, the way this works, it's all digitized now. It's all done by computers. When these earthquakes occur, there are seismometers all over the world, and they can very quickly pinpoint where these earthquakes happened. And in the future, you know, and this already exists, what I'm about to say, already exists in some cities that are really, uh, earthquakes happen fairly frequently. You can get out a text message system that says there's an earthquake that's about to occur, because they'll detect where it happens, and your text can get to you faster than the earthquake wave will, which is pretty impressive. Again, this is basically everything I just said. So, we know how to figure out where an earthquake occurs based on listening to these waves and the little squiggly lines on the seismograms. What about size? What about how much damage they do? Well, there's basically two different, boy, that's a bad two. Two different scales that are used to talk about how much damage an earthquake can do. The one you're not used to hearing about, normally you hear about the, you know, it was a 5.0 magnitude or a 6.0 or the 7.5 or whatever. That's the second thing I'll talk about. First thing is called the modified Mercalli scale. And it sort of, it's a relative measurement for earthquakes, and it's basically what you feel. So it doesn't necessarily tell us the amount of energy that's released. It's not very, it's not quantitative, it's qualitative. So it's not really analytical. It's more of, you know, how did things feel. So how does that work? Well, let's take a look at, let's assume we have an earthquake here in South Carolina, which occasionally occur. I'm not even sure why earthquakes occur here, but here at the epicenter, it would be a 10 and a 9 if you had a large earthquake here. And then you'd feel it all the way out here, even a little bit into Arkansas to these 2s and 3s. Gotta sneeze. And so what do these numbers mean? Well, here you go. So you can pause this and read through all these if you want, or you can go look at them on the slides. So a 1, it's not felt except by very few under especially favorable circumstances. So basically, if it feels like a 1, then you almost don't feel it, right? This is like you're sitting in your house and you're like, I think I felt something. And later on you hear on the news that, oh, there's an earthquake. I think I felt that. So a 2 is basically a few people kind of felt it, especially if in the upper floor in a building. 3, it's quite noticeable, so on and so forth. Number 6, everybody feels it. Many are frightened and run outdoors. Furniture is moved. Some plaster falls off. I think this is the biggest I've ever felt. Somewhere maybe between here and here. 7, everybody runs outdoors. The damage is negligible in buildings and of good design and construction. Slight to moderate, well-built, ordinary, etc., etc. Actually, maybe I felt that. I don't know. Somewhere in there. This is back when I lived in Alaska. Alaska's got a lot of earthquakes. So on and so forth until you get to like 10s and 12s, or, you know, basically everything's obliterated. But again, this is not the Richter scale, which is the other thing. This is the Mercalli scale. It's basically a measure of intensity, and it's based on, you know, what we would feel. The Richter scale is actually measuring, it's more of a quantitative thing. So it's measuring the magnitude of the amount of energy that an earthquake releases. Here, I want you to remember this. I want you to remember this. I want you to remember this. I want you to remember this after you leave this class. It is a order of magnitude. That means an earthquake that is a 2.0 is 10 times stronger than an earthquake that's a 1.0. Okay? An earthquake that is a 3.0 is 100 times stronger than a 1.0. It is an order of magnitude higher. When somebody says something is an order of magnitude higher, it means that it's 10 times larger. So even though this is only a number, number one higher, this is 10 times larger than this. This is 10 times larger than that. And a 4.0 is 10 times larger than a 3.0. But a 4.0 compared to a 1.0 is 1,000 times different. It is so much more energy is released in a 4.0 versus a 1.0. So when you hear about earthquakes that are a 7.5 versus a 6.5, a 7.5 earthquake releases so much more energy than a 6.5. It's a big difference, and especially when you start talking about huge earthquakes like 8.0s and 8.5s and things, it is an insane amount of energy that is released from these earthquakes. A lot of rock is moving past one another when these earthquakes occur. Okay? Okay. So this is just a diagram that kind of shows the relative amount of energy that's released. So here we have these orders of magnitude for these earthquakes, the Richter scale, and there's some comparison over here of the equivalent amount of energy released in other disasters. So basically, a large building blowing up is about the same as a 3.0. So 3.0 is not really that big of a deal. An average tornado, the amount of energy released along, and it's kind of a weird thing to use, but the amount of energy released from an average tornado is about, high 4s. When you get up into these areas, you're talking about a lot of energy released, and a 6 point something is equivalent to, a small atomic bomb. And then when we get up here, we're comparing things to, massive nuclear explosions or large volcanic eruptions. Then when you get up to this area, the 9.0, 10.0, these earthquakes, there's not really anything comparable to them. It is an insane amount of energy that gets released in these historical earthquakes. Okay. This is a video I will post. Normally I show this in class, but it really hits home how much energy is released in these earthquakes, in the different sizes. So we know how to find where earthquakes occur. We know how to measure them, or how they can be measured. Where do they occur? Well, first off, most of the earthquakes, and we're just going to look at the U.S. here, most of the earthquakes in the U.S. occur in Alaska. 1, Alaska is really big. 2, Alaska geologically is like a train wreck. There's a lot going on in this part of Alaska. I used to live here. There's earthquakes quite frequently, and it's fun that I get to hold that over anybody from California, because Californians think they feel a lot of earthquakes, and sometimes big earthquakes, and tough beans, Alaskans deal with much larger earthquakes. So anyway, Alaska gets to make fun of Texans because Alaska is bigger than Texas. But we also get to make fun of Californians because our earthquakes are bigger and more numerous as well. But I'm not really an Alaskan. I just lived there for a few years. Anyway, so the most earthquakes occur in Alaska. Large seismic risks are hazards. They exist along plate boundaries. So part of the reason they are so prevalent over here on the west coast in Alaska is because these are plate boundaries, right? There's a subduction zone going on over here where the plates are moving into the continent. They're getting subducted, and there's even volcanoes along here. And so you get a lot of earthquakes because you've got two plates scooting past one another. There's a lot of friction. In addition to that, though, there's also the New Magic Seismic Zone, which occurs in eastern Arkansas. And it is a potentially very hazardous area, for one, because there's just not a whole lot of earthquakes that occur over there. But historically, there have been some very, very, very massive earthquakes over here. There's a little bit of an area here as well, and I'm not even sure what's going on over here. I should go read about this one, but what's kind of going on here, and again, this is still being studied, and I even see new research that comes out of here where they argue that, yes, it could potentially have larger earthquakes in the future, or no, we don't think it's actually going to have larger earthquakes in the future, which I think is what the more recent research is saying. But I've had students who come from over here and who live over here, and there are earthquakes that happen fairly frequently. They're just smaller. Why is this here? I've heard this attributed to the fact that the Gulf of Mexico is actually kind of a failed rift, or it was originally part of a rift that opened up, and it sort of wanted to keep on opening up this way, and it just never quite split apart along here. And we do know there's a big rift in the Gulf of Mexico when North America split off from South America. But when you get these rifts, they typically occur on three points, and one of them will usually be sort of a failed rift. So that's probably what's going on here. Sort of a fun thing if you want to see how this occurs. If you go look at the Middle East on the east side where the Red Sea is. If you look at the Red Sea, and I don't have a picture right now, but if you look at a picture of the Red Sea, it kind of looks like this. And that's kind of that triple junction, right? And one of these is sort of a failing part of that rift. What's neat is you can also see this feature if you go walk around parking lots and you go look at the way the asphalt in a parking lot will split apart. You'll see that it kind of does the same thing. You'll see that there's usually two parts of these little triple breaks, and these two will actually be wider than the other one, and that's because this one's kind of failing. Well, this was sort of the failed area here, and it never quite fully split apart. And I've even heard that the Mississippi River exists where it does because there was some splitting here. And wow, let me just erase this. So there was some splitting that occurred along here, and it created a low area, and that's why the Mississippi River sits where it sits, which is pretty fascinating stuff. That, we kind of live close to this, and it's kind of a big geological deal. But this is a large hazard, and it's not like we're California, which puts a whole lot of attention into how they build things based on earthquakes. We don't necessarily do that here. St. Louis doesn't pay too much attention to that. Memphis doesn't pay too much attention to that. And so if there was another large earthquake that occurred here, you could see a ton of damage that occurs in these cities that are nearby, one. Two, you'll notice that the earthquakes here, the hazards here, are kind of confined here. They don't really spread out too much. Whereas here, you can see they spread way out. And that's partially because our rocks around here are flat and cold and hard, and they're not all that fractured. So if you have an earthquake here, those waves can travel through the rock fairly easily. And a good way to think about this is imagine a very long table. I can smack one end of the table, and the other end of the table will feel it 20 feet away. Over here, imagine having a whole bunch of tables all stacked onto each other, and they're all kind of broken up and everything. And if I smack one of them, it's not going to feel it at the other end of the pile of tables very well because you're just not transferring that energy very well. The same sort of thing happened. There was an earthquake that occurred, actually probably here, about 15 years ago or so, and the whole eastern seaboard felt it. It was only like a 5.0. It was not that powerful of an earthquake, but everybody felt it because a lot of the rocks around here are fairly flat-lying, and so they transmitted that energy in those waves fairly efficiently. Anyway, I could talk about this map all day. So, thinking about the Mercalli system, what would a large earthquake feel like if one popped in the New Magic Seismic Zone over here? And so this is based on an 8.6, which is a very large earthquake, which is probably what occurred in, I think it's like 1812 or 1811. There was a massive earthquake that occurred over here, and it was very well recorded in history. And we're worried that someday that could happen again. So let's assume that it did happen again. What would we feel? And I mean, I own a house over here. I had to decide whether I wanted to pay earthquake insurance or not. And so I'm not really too worried. There's small earthquakes that occur in Oklahoma. A lot of that has to do with the drilling that happens over there, but they're small. But I'm more concerned with this, and if we had a larger earthquake over here, could it hurt my house over here in Prairie Grove? So 8.6, so here's an 11. If you remember, an 11 is basically a lot of devastation. 10 is pretty good devastation. A 7 over here is basically you run out of your house and you're freaked out. And you might actually have some damage on your, chimney and some damage to your house and drywall and things. And a 6 is a little less damage, maybe a bookshelf falls over or something. So if we have a large earthquake over here, we could actually see some damage even all the way over here, at NWAC and Northwest Arkansas. And in the future, right now I don't pay for earthquake insurance, but in the future I'm probably going to, even though it's like $5 a month, I think, for my little frugal house. So for now I'm taking the risk, but in the future when I've got too much money, I'll probably just go ahead and pay the $5 just in case this ever happens again. But even if it did, there's a good chance my house would be just fine. So there's my unofficial professional opinion for if you guys should get earthquake insurance or not. Don't. This is not official recommendation. I take no responsibility if there's an earthquake and your house falls over. So earthquake-related hazards. I get into fun internet arguments with people over stuff like this. So the ground moves and it's dangerous. And one of the large hazards with earthquakes are fires, because earthquakes can break gas lines. They can damage electrical conduits. And so fires are a major hazard. If you're in a large building and an earthquake happens, yeah, you're kind of freaking out and worried about the building falling over. See here. But one of the major concerns you should have is a fire. Some other earthquake-related hazards, landslides can trigger, earthquakes can trigger landslides. We talked about that in mass wasting. Another thing that can happen is you can get liquefaction, which is something that I worried a lot about when I lived in Anchorage, because a lot of the sediment in Anchorage, Alaska is glacial till, right? There used to be a lot of glaciers around there, and there still kind of are. And all that glacial till is not very consolidated. It's not turned into a rock, so it's very loose sediment. Well, you shake that sediment around, and you can basically turn it into a liquid for a little while, and everything will flow. And it's very, very dangerous. And then, of course, just big cracks in the ground can also, be bad. But again, fire is a major thing. And liquefaction is a major thing when you live in a place where there's not a whole lot of consolidated, sediments. If your house isn't on a rock, you might worry about this. Probably don't worry about this too much in Arkansas, unless you live in the Mississippi embayment area, over near the river, over near the New Mexico seismic zone. But we're here on limestone and sandstones up in northwest Arkansas. I don't really worry about liquefaction. Landslides, maybe. Fires, yes, I worry about fires. Earthquakes can have a whole lot of aftershocks. So one earthquake will generate many more earthquakes. There's another video I'm going to post I'll get to in a minute, and I'll just talk about that when I get to it. Another major hazard that earthquakes can generate are tsunamis. We don't worry about these too much in Arkansas at all. But in the places I've lived, this is something I actually had to be concerned with quite a bit. I used to live in Hawaii. 4 days after I moved to Hawaii, to Honolulu, the 2010 earthquake and tsunami occurred in Japan. That tsunami came to Hawaii, and it did a reasonable amount of damage. Nothing like what it did in Japan. We actually got pretty lucky in Hawaii, but it did damage a small boat harbor pretty bad, and on a couple of different islands. Anyway, so how do tsunamis occur? I'll just blow up this picture here. So you get usually an oceanic plate that's being subducted underneath a continental plate. It pulls back that continental plate until there's too much pressure, and boom, it snaps back and it pushes the water that's above it up. This generates a tsunami. That pulse will then move out from that location, and when you're in the open ocean, you don't really see this pulse, because this is normally just a few feet, maybe 5 feet, 10 feet, and it's kind of hidden amongst the normal waves. But this pulse will move at the speed of a jet airliner. It moves at about 500 miles per hour. I think I've got that on the other slide. Yeah, greater than 700 kilometers per hour. So if you ever fly across oceans, that's about how fast these tsunamis move. And then when it gets close to the coastline, it slows down. It will sort of push the water up, because basically you've got 10 feet of offset in this water column. But as it gets shortened, as that pulse of energy gets shortened as you go this way, it sort of starts to push all that water up, and that's how you can get a 40-foot tsunami once you get towards the coastline. It sort of squeezes it all up there. When these tsunamis happen, one of the issues is it's not always the first wave that is the biggest. You can have multiple waves just like you have multiple normal waves in the ocean, and this is honestly what will kill a lot of people. You'll get a tsunami that happens along a coastline. You'll see the water pull back, and boom, big tsunami comes in, and then people come rushing in to help out or see the devastation, and then the second wave comes in, and it's even worse than the first. So if a tsunami's coming, don't get away. Get to higher ground immediately. One of the things I used to have to tell kids when I lived in Hawaii, because I used to be an educator out there, was like, if any of you kids are surfers and you like surfing, don't go out and try to surf a tsunami wave. They don't curl like these normal waves do. Basically what it looks like when you're out there is it looks like the ocean, it's like a short-term flood. The ocean just all of a sudden rises 40 feet. Or 30 feet or whatever it is. And they are waves in a sense, but the gap between the waves, so if these are waves, the distance between these waves might be as much as a mile or more. It's not like your standard waves, which are 10 feet apart. It is very, very, very far apart. And so as these waves come in, it's just 40 feet of water, and then it goes away, and then 40 feet of water, and then it goes away. It's extremely devastating. So in class, normally I'd show these videos. I'll go ahead and post them on the canvas, and you guys can watch them. Watch this video in particular. It is incredible. It gives you, it's actually a Japanese video, but it's very well done. And you can see in the video basically where this plate is subducting underneath the plate that Japan is sitting on, and it gives you a really good feeling for the tectonic movement that's occurring when these earthquakes happen. And so it also shows that it's not just a single earthquake. There was one large earthquake that occurred, but there's all these aftershocks, and there's even some earthquakes that kind of set it off. Anyway, go watch it. It's a really cool video. In fact, I'm going to ask test questions on it, or quiz questions on it. Probably test questions on it. So I'm telling you to watch it now. It will be on the test. It will be on the test. I will test you on it, and I'm telling you now. Those of you that don't watch this video will be sad. But those of you who are watching it will get to watch it, and it's really cool. And it just really brings a lot of these concepts together. This will be another one that I post, probably, I think. But it just shows the propagation of these tsunamis and how you can kind of see the pulse of waves. And these, tsunami, this was the one that was in Japan. It goes all the way across the ocean. We can detect it as it comes around South America. It's really small by then. It's kind of been reduced. But, I mean, tsunamis can actually reflect off of land surfaces as well. It's very amazing. So how deadly can they be? The 2004 Indian Ocean tsunami, for those of you that are about my age, you'll probably remember that. That's when tsunamis really got in, became a thing that got talked about a lot. It killed that many people, at least. For comparison, 227,000 people. The Civil War, about 600,000 soldiers died. Vietnam killed about 56,000 American soldiers. In 9/11, about 3,000 people died. So, the amount of death that we're talking about here is significant. Tsunamis can kill a lot of people. They are very deadly, and it's why we watch out for them. They are very dangerous. Uh, and honestly, I could do an entire chapter on them, but I'm not going to because we're in Arkansas, and there's just no tsunamis that exist in Arkansas. Or at least they haven't for, 300 million years. So, that is the end of the chapter. Like I said, I'll post some of these other videos. Go and watch them. Let me know if you have questions.